All right, so we'll take a look at some of the questions, sample questions from the week 9 mole and chemical formulas topics in ALEKS. And the first one here, we're asked to calculate and use the molar mass of the element. So it says a chemist weighed out 101 grams of tungsten. And we need to calculate from the grams of tungsten, we need to calculate the number of moles of tungsten that she weighed out. Okay, so what we're doing here is we're going to go from grams of tungsten to moles of tungsten. So going from grams to moles of anything, we're going to use the molar mass of that thing. In this case, it's of tungsten, which has the chemical symbol W, and we can look up the molar masses for individual elements from the periodic table. Okay, so on your data sheet here on the right side, you'll see there's a periodic table. Tungsten is right here in the middle, atomic number 74. We can see the atomic mass there is 183.84. So what does that actually mean? So this then tells us that 1 mole of tungsten W is equal to 183.84 grams of tungsten of W. Okay, and you can look that up for any of the elements on the periodic table. You don't need to memorize that. You always have a periodic table. You can look that up for any element there is. So we're given, we have 101 grams of W of tungsten. We want to convert this into moles of tungsten. And we're going to use our molar mass that we get from the periodic table. And we're going to take that, we're going to set it up as a conversion factor. Which we've done multiple times already. Now we're just applying that same concept to these molar masses. And to get the conversion factor, we just put one unit over the other. So 1 mole of W is 183.84 grams of W, or we can just simply flip it, 183.84 grams for every 1 mole. And we'll use the appropriate conversion factor depending on what unit we're given and what we need to find. Okay, so when we set this up, we always start with what's provided. We have our 101 grams of tungsten. We want to now use the most appropriate conversion factor. We're going to pick the one that has moles on top, because that's the unit that we want to end with. So 1 mole for every 183.84. The grams go away, and then we end up with moles of tungsten. You need to evaluate that using your calculator, and then make sure that you round to the correct number of sig figs. Okay, so just as a quick guide, a quick reminder, we have 3 sig figs here. In our molar mass, we have 5 sig figs. So in this case, our final answer needs to be rounded to 3 significant figures. All right, so in this one, very similar to the first question, here we're calculating and using the molar mass of diatomic elements. Okay, so let's remember that diatomic elements mean that those elements are found as groups of 2, as pairs. So for instance, we're told that we have 0.055 moles of iodine participate in a chemical reaction. So the iodine here, chemical symbol I, and as a diatomic element, right, that means it's going to exist as I2, meaning 2 atoms for every molecule of iodine. And we have 0.055 moles of this. We need to calculate now the mass of iodine that we have. So we want to go from moles to mass, which is in grams of I2. And just in the, like in the question before, going from mass to grams, or I'm sorry, moles to grams or grams to moles, we're going to use the molar mass of the thing in question, which in this case is iodine, I2. And again, we're going to use the periodic table to look that up. So I find iodine on the table. So iodine is here. So the molar mass for I is 126.90 grams, but I have two iodine atoms that make up a molecule. So the molar mass for I2 would be 2 times iodine, right? So we have here the 126.90 grams times 2, and that's going to give me do a quick calculation. Yeah, 126.90 times 2. That gives 253.80 grams of I2 for every 1 mole of I2. All right, and that's going to be our equality that we can turn into a conversion factor. So when we set this up, again, we start with what's given. We're given the 0.055 moles of I2, put that over 1, and then we take our equality, stick it in here as a conversion factor. If you want to end up with grams as our unit, we'll put the grams on top, so 253.80 grams of I2 for every 1 mole of I2. Moles cancel, and then we have our use our calculator, solve this, round it to the correct number of sig figs. In this case, we have 2 sig figs, and this number, we have 5 over here. So our answer should have 2 significant figures. All right, so in this one, we're going to be taking a closer look at the information provided in a chemical formula, and specifically how the subscripts give us a multimole ratio in that formula. So in this case, we have a molecule by the name nickel tetracarbonyl, and we're given the chemical formula for it. So we have Ni in parentheses CO subscript 4, and we're told that there are 11.1 moles of carbon in this sample of this particular compound. And then we need to figure out, based on that, how many moles of oxygen, so moles of O, are in this sample. All right, so the only thing in this question that relates the moles of carbon to the moles of oxygen is our chemical formula. All right, so the mole to mole ratio of the elements comes from the formula. So we're going to read the subscript specifically now, and we can see that for every one of the NiCO4 that we have 4 carbons. Okay, so we have 4 moles of carbon, is how we read that, for every 4 moles of oxygen. Okay, remember the 4 that comes outside the parentheses, everything in the parentheses gets multiplied by that. When you don't see a subscript, 1 is understood to be there. Okay, so that's why we times 1 times the 4 gives us 4 moles of C, and then 1 times the 4 here gives us 4 moles of oxygen. We can insert an equal sign here, and this looks just like a equality, which you can turn into different conversion factors. This is our multimole ratio of the atoms to each other in our chemical formula. We are told that in our particular sample that we have 11.1 moles of carbon to start with. So we're going to set it up. We're going to start with what's provided, 11.1 moles of C. That goes over 1. The relationship between moles of carbon and moles of oxygen is the subscripts in the chemical formula. We have that established already. We now insert that as a conversion factor. If you want to end up with moles of O, that goes on top. So 4 moles of O on top for every 4 moles of carbon underneath. Moles of carbon go away. 4 cancels out, and then we end up with the same number as the moles that we started with. So we should have 11.1 moles of oxygen in that sample as well. All right, so in this question, we're going to be taking a look at finding molar masses from chemical formulas. And this is just an extension of identifying or calculating the molar mass of individual elements. And we saw that previously we were able to find those simply by looking at the periodic table. And we're going to do that again in this case. So we're told the chemical formula for urea is NH2 in parentheses and then twice, and then we have a CO right after it. So the molar mass of this is by definition the mass of 1 mole of our compound urea NH2 twice, and then we have CO. So what we need to do then is to take a close look at our formula, chemical formula, and figure out for every 1 mole of this entire thing, how many moles of these atoms do we have? And that's where the subscripts are going to be important. All right, so based on this, the formula is telling me for every 1 mole of urea, I have 2 moles of nitrogen. I have 2 times 2, which is 4 moles of H. I have 1 mole of carbon, and I have 1 mole of oxygen. And this is all for 1 mole of urea. So all I need to do then is to look these individual molar masses up. So look up the molar masses for the elements from the periodic table. And then insert them into my calculation. So I have 2 times the molar mass of nitrogen. So using a periodic table, we can see that nitrogen has a molar mass of 14.01. I have 4 moles, so 4 times the molar mass of hydrogen, which is 1.01. I have 1 carbon. Carbon is 12.00. 12.01, sorry. And then oxygen, we have 1 oxygen, and that's 16.00. So we add these up, and then we simply sum them all together at the end. And whatever we get, that's going to be your molar mass. So 14.01 times 2, that's 28.02 plus 4.04 plus 12.01 plus 16.00. So I'm just going to do this in my head really quick. 4, 5, 6, 7. So 0, 10, and 10 is 20. So 2, 4, 5, 6. Okay, so 60.07. So this tells me that for every 1 mole of urea, if I had 1 mole of it, it would weigh 60.07 grams of urea. Another way of stating that is that the molar mass of urea is 60.07 grams per mole, right? Or sometimes you'll see 60.07 grams times moles to the -1. That means the same thing. It's just a different way to represent the same unit for molar mass, which is grams per mole. All right, so now we'll take a look at another piece of information that we can extract from the chemical formula. So here we're trying to find the mass percent from the chemical formula, and we're provided with a compound, chromium-3 carbonate, and we're provided with the chemical formula, Cr2, and then CO3 3 times. And we need to calculate the mass percent of oxygen. So oxygen is O in this particular compound. All right, so we've seen percentages before. We've worked with them several times. So if we're looking at the mass percent of oxygen, what this means is that we're looking for the mass of O, so the part divided by the whole thing, which would be the mass of the Cr2, CO3 3 times. And because it's a percentage now, whatever number we get, we're going to multiply it by 100. Okay, so where are we going to get these masses from? Well, the easiest thing to do is just to assume you have 1 mole. of your compound. Okay, so in 1 mole, just like we did in the previous question, in 1 mole of Cr2CO3 3 times, we have 2 chromiums. We have, so there's the 2 chromiums. We have 3 carbons. And then we have 3 times 3, which is 9 oxygens. Okay, and then we look these up in the periodic table. Right, periodic table is very helpful for us in a variety of ways. This is just one of them. So chromium, 51.99. We'll say we'll round that to 2 decimal places. So 2 times 52.00. You have 3 carbons. So that's 3 times 12.01. And then 9 oxygens. Oxygen is 16.00 times 9. All right, so then we'll just stick that in our calculator, and we can determine the overall molar masses. All right, so if we have 2 times 52, that's going to be 104 grams. We have 3 times 12.01. Okay, so that's going to be 36.03. And we have 9 times 16, which is 144. Okay, so we add these together. And we get 284.03 grams. That's the molar mass of our compound. And that is the total mass of 1 mole that would go in the denominator. Well, guess what? We already figured out the mass of the part, the mass of the oxygen. That's this thing, which we figured out was 144. So we've actually have all the parts to this question already figured out. We just need to do the correct operation. So the mass percent now of oxygen would be the mass of the oxygen in 1 mole. So we have 144.00 grams divided by the mass of 1 mole of the entire thing, which we found as a molar mass, 284.03. And then as a percentage, we're going to multiply that by 100. Grams go away. So 144 divided by 284.03. And then we times it by 100. Okay, and that's going to be 50, about 50%. Let's see, we have 1, 2, 3, 4. 50.70% oxygen in our sample of chromium 3 carbonate. So in this case, it says to round it, your answer to the nearest percentage. So this would be rounded up. This would be 51% as the solution. All right, so in the next question, we're taking a look at determining a molecular formula for molar mass and elemental analysis of binary compounds. So in these questions, you're provided with the molar mass of whatever it is that we're dealing with. So in this case, the molar mass of compound X is 283.89 grams per mole. Remember, molar mass, we get that by simply adding together all of the atoms that we have in that chemical formula. Now, we're also given some elemental analysis. We're told that this compound is made up of phosphorus, P, and oxygen. And we're given the mass percent of each of these. So 43.64% of this compound is phosphorus by mass, and the remaining 56.36% is oxygen by mass. So how can we use that information to determine the molecular formula? Well, we first of all need to convert this information into moles. So the best way to do this is to just assume, again, you can assume any sample size, but it makes sense because these are percentages. We assume that the sample size is 100 grams. So if I have 100 grams of the sample and 43.64% of it is phosphorus, that means then that the mass of P in the sample is 43.64% of 100, which guess what is 43.64 grams of phosphorus. And because there's only the only other element present here is oxygen, that means that the remaining mass will be oxygen. All right, so I can just either take the percentage that's provided, or we can just do a simple subtraction. So 56.36% of the assumed 100 grams is going to be oxygen. So that's 56.36, sorry, 56.36 grams of O. These are going to be important because now we have grams of each of these. We can now convert them to moles. Because what we're trying to do is to get a mole-to-mole ratio, okay, of each of these components. So I have now 43.6. Let's color code this so we can keep them separate. If I have 43.64 grams of phosphorus, okay, to get to moles, I'm going to use the molar mass of each of these things, and I get those from the periodic table. So phosphorus P is, molar mass of that is 30.97 grams. Okay, I put the 30.97 on the bottom. For every 1 mole of phosphorus on top, grams go away. Okay, and then I get a number for the number of moles, 43.64 divided by 30.97. Okay, and that's going to be 1.4, I'd say 1 moles of P. I do the same thing now for the other component, the other thing that we have there, which is the oxygen, right? So I have 56.36 grams of O, put that over 1. Use the molar mass of O now, which is 16.00 grams of O for every 1 mole of O. Grams go away, and I just divide now the 56.36 by the 16. 56.36 divided by 16. It's going to give me 3.52 moles of O. So what I have to begin with is a rudimentary mole-to-mole ratio. I can maybe now start writing a chemical formula. So I have P, and the mole there is 1.41, and then I have O. The moles there are 3.52. Right? Obviously, that is not a proper chemical formula. Right? I need to have whole numbers. So the best way to do this is to divide both of them by the smaller of the two numbers. So the smaller of two is 1.41. We divide both of them by 1.41. By doing that, we make sure that that first one has a subscript of 1. And then if I do the same thing for the oxygen now, I have 3.52 divided by 1.41, and that gives 2.50, right? So the mole-to-mole ratio now looks a little bit better than it did previously, but it's still not a whole number ratio, right? We still need integer ratios, whole number ratios. How do we convert now these to whole number ratios? Well, the first one's already a whole number. The 2.5 is not. So the easiest way to do that when you have a 0.5 in something is just to multiply it by 2 to get the smallest whole number. If I do that for the first one, I also need to do that for the second one. So 1 times 2 gives me 2 as my subscript now for the P. And then for the O, 2.5 times 2 gives me 5. Right? This ratio here, that's the smallest whole number or integer ratio. That's called the empirical formula for this compound, all right, made up of phosphorus and oxygen. So from this empirical formula, I can now calculate the empirical mass of this simply now by looking at that formula. Okay, so I have 2 phosphoruses and I have 5 oxygens. I look these up on the periodic table. All right, oxygen is 16 times 5. And then my phosphorus, we said was, what was that? 30.97 times 2. So we add those together. So 30.97 times 2 gives 61.94. And then 5 times 16 gives 80.00. So I add these together and I get 141.94. And this is grams per mole, and this is the empirical mass of this compound. Okay, and the empirical just means the smallest whole number ratio. So 141.94 grams per mole. So in this question, I'm also told that the molar mass, the actual molar mass, when I add together the number of each of these types of atoms is 283.89. Okay, what I can do now is to use those two numbers to get a multiplier to multiply the subscripts of the empirical formula by. Okay, so how do we get that multiplier? We're going to take the molecular mass, or the molar mass, and we're going to divide it by the empirical mass. Okay, so my molar mass was provided. It was 283.89. And my empirical mass I just found is 141.94. And typically when you do this, you should get either a whole number or you're going to get something really, really close to a whole number. So 283.89 divided by 141.94 gives me 2.00 ... Okay, so my multiplier here is 2. So I'm going to take now my empirical formula that I calculated before, P2O5. And what I'm going to do is multiply each of these subscripts by that multiplier, which is 2. Okay, so now I end up with 2 times 2 is 4, and then 5 times 2 gives me 10. So P4O10 then would be the molecular formula for this compound X, whatever X is. In this case, we just found it. P4O10 tetraphosphorus decoxide, if you had to name it.